Hi, this is the second part of the lesson on the South Wales coalfield. What I want to do is go through some of the work you've been doing, answering the questions about the geology of this area. The first question was looking at the regional fold. As you can see from the cross section, this is synclinal. Well, to be more accurate, it's informal, but we do have the oldest rocks there on the edge of the structure, the youngest rocks in the middle, which does make it obviously a syncline as well. The stress that formed this, because of the roughly east-west axis we can see at the fold, must be north-south. And that's fairly typical of Variscan structures, certainly in southern Britain. Now, part of this coalfield is going to be inaccessible. There's a limit of maybe about 1,000 metres, maybe a little bit less than that, that a deep mine can actually be dug to. So anything beneath that, any of these deposits, even as you can see some fairly valuable ones, are going to be inaccessible. It's not going to be possible to extract this coal. Although interestingly, there's work being done to try to extract the methane from these deep coal seams to use as a perhaps more modern, cleaner fuel than the coal. I did ask you to then have a look at the different ranks of coal. If we look at the boundaries between each of these ranks and link them back to the elements that would be in it, we can find, for example here, anthracite is going to have a maximum of 10% volatiles. So it'll be 90% or more carbon. Bituminous coal is about 20%. We don't need to worry about the high and low volatile part. Subbituminous coal takes us to about 32%. And then the largely useless lignite is about 48%. Any more volatiles than that, the material then is peat. So, having worked this out, we can then apply that to the coalfield itself. Because we can see, looking at these particular coal seams, that the percentage of volatiles in the coal is far from consistent. We have some lignite, some subbituminous coal, the bituminous coal, that's the famous Welsh steam coal that was exported around the world, has even been found on the Titanic. And finally then the very high value, very clean burning anthracite that we find particularly in the northern part of the coalfield. It was this anthracite that formed the last resources extracted from the coalfield in places like Tower Colliery in Hawaii, right up on the northern edge of the coalfield. If we look at a map here, looking at the volatile content for one particular coal seam, we can see their location X has a content of about 31%, so that's going to be a subbituminous coal. And if we look at where the anthracite will be found, as we've said, we've already identified it in the north there. We can identify an area there somewhere between the 9 and 11% isovol, and we can shade that area in to the north of it. So, the South Wales coalfield has been studied in an enormous amount of detail. Some of the old coal geologists' work on plotting individual coal seams is really quite remarkable in its detail. We do need to think, though, about these patterns. Why we have the patterns that we do. So for my conclusion, what I'd like you to do is to think about what could cause these differences in rank between the different parts of the coalfield. We know they're there, but why do you think that is? See what you can come up with, and we'll talk about it next time I see you in class. I'll see you then.